All right, so in the last section, we are going to wrap up chapter 8 talking about covalent bond strength. And so what we're doing in this section is we are simply going to calculate how much energy is required to break bonds when we have a chemical reaction occurring, and how much energy is kind of given back when we have the reformation of chemical bonds in the products. Okay, so the strength of a bond is measured by determining how much energy is required to break the bond. Early on, especially when we start talking about the section on multiple bonds, we talked about how energy has to be input into breaking bonds. I used the meter stick, and I said every time, no matter if it's just the single meter stick, you have to input energy to break it. But the more bonds that you add, the more energy it takes to break those multiple bonds. And so what we're going to be calculating is called bond enthalpy. As an example, if you look at this equation up here, where we have a chlorine to chlorine bond. Okay, it's connected, those two chlorines are connected by a single bond. In order to break those bonds, it requires 242 kilojoules per mole of energy to break those bonds and form single atoms. Okay? Now, it's probably difficult to see on your notes, especially up here. So right now, once you open your books, if you need a book, I got to over here by Olivia Holland. So go ahead and grab one, and then open up to section 8 and find table 8.4. Give me a moment to get there. Page 330. Page 330. And before you get excited in anticipation of hopefully, spending time and memorizing this table, you don't have to. Okay. I give this table to you if you need it. So, again, another bummer for you that you don't have to sit at home and make flashcards for this. Anyway, what this table is showing us is a list of average bond enthalpies. Now, remember, I said average bond enthalpies. Okay. We'll see why it's an average value listed here, I believe, on the next slide. But if you look at the table, you'll see that all the values for these various bonds are positive. That is because bond breaking is an endothermic process. Energy has to go into the system to break the bonds. Okay? When I said average, that's what it is, because even though we have a single value listed for a type of bond, for instance, the carbon-hydrogen bond, okay? First of all, locate the carbon to hydrogen bond and tell me the value. What? 413 kilojoules per mole, okay? That's the average. But if we were to look at the carbon to hydrogen bond in methane compared to the carbon to hydrogen bond in chloroform, the values or the amount of energy that is required to break those bonds are going to be slightly different. Okay? So scientists, thank you. They went ahead and created the data to where we can just use the averages to get a pretty good idea of what we could expect the energetics to be in a chemical reaction. Okay? Now, another way, the way that we're going to do and solve for the enthalpies of reaction is this. Is we're going to estimate the delta H for a reaction so we can compare bond enthalpies of the bonds that are broken to the bond enthalpies of the new bonds formed. Now, thankfully, whether you break a bond or you form a bond, that energy values that are listed in table 8.4 don't change. Okay, it's all the same. So you want to highlight, star, arrow, whatever this formula is here. Okay, because this is what we're going to use. When we're talking about bond enthalpy, we're going to be using the enthalpy of reactions where we have the sum of the bond enthalpies that are broken. And from that, we're going to subtract the bond enthalpies of bonds formed. So enthalpies of bonds broken minus the enthalpies of bonds formed. So we're going to be looking at basically reactants minus products. Okay? Now, there's really two ways that you could go about this. There might be more, but we focus on two. Okay? So if we look at this reaction where we have methane, CH4, reacting with chlorine, Cl2, they yield the product CH3Cl plus HCl. So they have a formation of two compounds, one of them being a strong acid. So this is also where Lewis structures are very handy. Okay? When you go to solve these types of problems, it is pretty much imperative that you do the Lewis structures for all reactants and all products. It'll make your day that much simpler. So this is the first method that you can go about solving this. So if you were to do, eventually, if you did this long enough, you'd be like, well, I don't have to do Lewis structures. I can just visualize it in my head, okay, and see who's going where. They say that one carbon to hydrogen bond and one chlorine to chlorine bond are broken. Because if you look at what is in our reactants compared to what is in our products, here we had CH4 in our reactants. In our product, we had CH3Cl. That means one of the hydrogens had to be kicked off and replaced with the chlorine. So that means a carbon to hydrogen bond had to be cut and broken, and the chlorine to chlorine bond had to be cut and broken. So they are free to go about wherever they need to go. Excuse me. And so that hydrogen that was kicked out needs a home to go to. So it finds the remaining chlorine. They say, hey, buddy, how's it going? They come together and form a compound. So we had a single carbon to hydrogen bond broken and a single chlorine to chlorine bond broken. But then we had the formation of one carbon to chlorine bond made and the formation of one hydrogen to chlorine bond made. Okay? So we do a kind of an intermediate setup. Okay? What is this first part of that formula again? It's bonds, what? Broken. Okay? So here's that single. And these capital letter D's, those are just a stand-in, because there'll be times where you have to break multiple bonds of the same bond. And so let's say we had to break 2 carbon to hydrogen bonds. Instead of a D there, you'd have 2. Okay? It becomes a multiple. All right? So we had the single carbon to hydrogen bond broken. We had the single chlorine to chlorine bond broken. Okay? We use table 8.4 that you have your book open to and substitute values. Again, chlorine to chlorine is 242 kilojoules. Carbon to hydrogen is 413 kilojoules. We sum those up. Okay, we get 655 kilojoules. We subtract from that the bonds what? The bonds formed. Okay, again, we had to reform a carbon to chlorine bond, and we had to reform a hydrogen to chlorine bond. Carbon to chlorine is listed as 328 kilojoules. Hydrogen to chlorine, 431 kilojoules. Sum them up. And then it's just a little bit of math. Okay? 655 kilojoules minus 759 kilojoules, we get an overall enthalpy of the reaction of negative 104 kilojoules. Is this process, or this reaction, endothermic or exothermic? Exo, why do you say exo? It's because it's negative. Very good. Yeah, negative results are exothermic, meaning energy, or probably in this case, heat, is given off. And positives are endothermic, meaning energy or heat is absorbed. Okay? Also in, I think it's in the, do you have a table 8.5? Okay. But yeah, I think it also is 8.4 also give you the multiple bonds. Yeah, 8.4 also has multiple bonds associated with it on the very bottom. But you also have 8.5, which I think is just a larger version of it. Okay, that's what I thought. Okay, so again, for example, as to show you the increasing amount of energy required, a single carbon-to-carbon bond is, well, these are bond lengths. We don't need to worry about that. We don't need to worry about that. Sorry, I thought it said energy values. So 8.4 is what you need. 8.4 is what you need. Okay? You'll see there when you look at two atoms. So again, if we look at the carbon-to-carbon bond on 8.4, if there is one listed, you'll see as you increase the amount of bonds there, you're going to increase the amount of energy required to break them. Okay? So let's do a couple of examples here. I'm going to write this practice one, excuse me, on here, because I'm going to kind of show you how I like to do these and why it's important to have a Lewis structure available to do this. So I'm just going to take a moment to write this. Da, 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 da. Da, 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 da. Oops. 4. Okay. This is what we have going on. I'm going to try to reduce that glare here. Can you still see it in the back? Yeah, okay. All right. So in the first example that we saw with the CH4 and the Cl2, okay, they didn't bother doing Lewis structures because, you know, again, after a while, once you start comparing what you start with and what you have, you get to see who's actually being moved. Okay, but that method doesn't tell you, is there a double bond? Is there a triple bond? That's why Lewis structures are important, because you develop an idea of, are there multiple bonds between atoms? Okay, now you could create that the Lewis structure equation like we see here for that first one, and do it one at a time like we saw with the first one. But for me, the problem is if you miss a bond that breaks or a bond that forms, your calculations aren't going to be correct. So what I do, and what I encourage you to do, but you can do however you want, is to assume that all bonds break and all bonds reform. That way you don't miss anything, okay? And I like to do a fun little visual when I do this, okay? Well, first, let's start setting this up, okay? First of all, delta H, okay? So let's look at the bonds broken. So I like to play, I don't know, I guess you could call it Fruit Ninja. You guys remember Fruit Ninja? Okay, we slash, right? So I'm going to start slashing bonds. So I've got carbon. Let's look at the carbon to hydrogen bonds, okay? So I've got 1, 2, 3, 4, 5, 6 carbon to hydrogen bonds that I just broke, right? Slashed. But what do you notice is in front of that compound? What's that? What does that mean? Yeah, it means there's 2 of these molecules present. So I have to break those bonds as well. So I cut 6 in 1, 2 present. So that means I have 12 carbon to hydrogen. Okay. And right now I'm just kind of setting it up so that I can substitute values in. I'm getting a visual of what bonds I broke. Okay. Plus, okay. Is there another bond that needs to be broken in this molecule before I move on to the next? Carbon to carbon. And again, there are 2 of those. So 2 times a carbon to carbon. And we've got one more. We've got oxygen to oxygen. Okay, this is basically that. Okay, single bond. So, yeah, I didn't do the full Lewis structure because I don't need to do the dots. I just need to look at the bonds. So I break that. That's a single. But how many are present in the reactants? 7. Okay, again, we have O2 here. That means 1, 2 oxygens. But there are 7 of these molecules present. So I broke 1 bond here. That means I have to do it 7 times. So 7 oxygen to oxygen. And that takes all of our reactants. Okay? So let's move on to the products. These are bonds being formed. So we do it one at a time. Get over there. Okay. So here we have a carbon to oxygen double bond. We've got 2 of them per molecule. So, okay? But how many of these molecules are present? 4. There are 2 oxygen or carbon to oxygen double bonds in a single molecule. There are 4 present. So how many double bonds did I just break? 8 times 2 or 4 times 2 is 8. 8 carbon to oxygen double bond. Notice how I indicated it's a double bond in here as well. That tells me I need to look at different values. Plus, excuse me, we have H2O. Okay. We got hydrogen to oxygen single bonds. We got 2 of them. Slash. So we had 2 hydrogen to oxygen single bonds in 1 molecule. There are 6 molecules present for a grand total of how many single hydrogen to oxygen bonds did I just break? Or sorry, form. My apologies. Form. How many did I form? 6 times 2 is 12. 12 hydrogen to oxygen. And that's all the bonds there. Okay? So this is kind of what it should look like to help give you a visual of what values you have to look up. Okay? So we're just going to proceed to do that. Okay? So again, I got 12. What is the carbon to hydrogen value listed in table 8.4? 413 kilojoules, okay? Plus 2 times carbon to carbon. is what? What was that? 348? 348 kilojoules plus 7 oxygen to oxygen single bonds. 146? 146 kilojoules. Okay? Minus from that, 8 times carbon to oxygen double bonds. It could be also listed as oxygen to carbon. Doesn't matter. So what's the value there? It's going to be in the bottom portion of that table under multiple bonds. Say that a little bit. 1,072. 799. All right. 799 kilojoules plus 12 times hydrogen to oxygen single bond. What do we have there? 363? Yeah. 4, 6, 3. All right. Okay. So I don't have a calculator within a foot of me, so I'm going to ask for your help. So now we have to start multiplying our values. Okay. What's 12 times 4, 13? 4956. Okay. 4956 kilojoules plus 2 times 348. 696 kilojoules and 7 times 146. 1022. Okay. I'm doing these in baby steps just so we don't go crazy here. 8 times 799. 6392. That's in kilojoules. Plus 12 times 463. 5556. All those numbers look correct. I think so. Okay. Almost done. Now we have to sum up this first part. What do we get? $66.73. 74. I was off by 1. 74 kilojoules minus. And then the sum of the products. What do we get for the sum of the products? 11,948. Okay. Last step. Take 6,674 kilojoules minus 11,948 kilojoules. Negative 5,274 kilojoules. Endothermic or exothermic? Exothermic, exactly. It's got the negative sign. This is a combustion reaction. Okay, we have a hydrocarbon plus oxygen and yields CO2 and H2O. So the number we get here, it's pretty high number, highly exothermic, and that's what we would expect with a combustion reaction. So it makes sense. Okay. Let's do one more problem before we wrap up this chapter. Okay, and this is going to be from your notes. So again, under practice exercise here, I'm just going to write this down real quick. We've got N hydrogen, hydrogen. I would copy this. Well, I guess you don't have to if you have enough room that's there, but if you want to, you can. Nitrogen, nitrogen, triple bond plus 2H2H. Single bonds. Okay. So what we have here is, to refresh your memory, a decomposition reaction where we have one substance breaking down into its component substances. Okay? So let's start breaking bonds first. Okay? Let's look at the nitrogen to hydrogen bond. Cut, cut, cut. So how many did I just cut? 4. So I put 4 here. And there's no coefficient out here, so we don't have to worry about multiplying anything like that. So there's just 4. And what is the hydrogen to nitrogen value? 391. 391 kilojoules. Okay. And really the only one we have left here is a nitrogen to nitrogen single bond. We cut that. And what is its value? 162? 3? Okay. 163. And there's only one of those, so not even going to worry about that. And that's all we have on the reactant side. Okay, so I close up my brackets, subtract, bonds formed. Nitrogen to nitrogen triple bond. We got to break that. What's its value? 941. Again, there's only one. And then a hydrogen to hydrogen single bond. There's 2 of them. So we have to put 2 times whatever H to H is. For 36. Okay. So we then start multiplying what we need to. 4 times 391. And we can actually kind of simplify this in fewer steps. Take 4 times 391 plus 163. $17.27. And then take 2 times 436 plus 941. Did you get 1813 for that? Okay. So now take 1727 minus 1813, and that's our answer. Negative 86. And don't forget your label. You can label this as kilojoules or kilojoules per mole, but just putting kilojoules is plenty fine. Okay? Questions on that? Not too bad. Not too bad. Okay. But again, you see the importance of, or the I guess, nicety. I don't know if that's a real word, of having Lewis structure so you can visualize cutting and breaking those bonds and forming those bonds. Okay. Well, that wraps up chapter 8. Tomorrow, again, if you can, watch the video from yesterday. That should help you with some of the questions from the practice worksheet. We'll go over that tomorrow. You'll turn that in. Then I'll give you your next stuff dealing with the last half of chapter 8. Again, I'll let you work with partners if you want to. And that's a wrap.